at the beginning, I would like to thank the organizing committee for the invitation me to this seminar and the possibility of presentation our results. I come from Poland, from the Jagiellonian University of Krakow. We started IR studies of a source molecule at 64. And the first papers I read at that time were the papers of Dr. Eichens. Even now I'm using some of the spectra taken from Dr. Eichens' papers in my monographic lectures of catalysis and spectroscopy. I showed some spectra which were presented today by Dr. Hall for my lectures. A few years ago I had the possibility to work with Dr. Eichens at Lehigh University for 2 years. And so it is a great pleasure and honor for me to participate at this meeting. We apply IR spectroscopy to the problem of zeolites. We study the properties of acid site in zeolites and their interaction with reagent molecules. We studied the concentration of both Brensted and Lewis acid sites by quantitative IR studies of sorption of ammonia and pyridine. We studied the acid strengths of Brensted acid sites of hydroxyl groups and their heterogeneity. My today presentation will concern the problem of heterogeneity of hydroxyl groups in zeolites. We study also the interaction of acid sites, the properties of which are already characterized with the reagent molecules. We made a study of interaction of acid sites with olefins, alkenes, and now we are studying alcohols. Our IR results concerning the properties of hydroxyl groups are compared with the results of quantum chemical calculations. We do semi-empirical MNO calculations and ab initio calculations, and compare the results with IR data. We calculate the deprotonization energies of OH and the stretching frequencies and compare the calculated the values with experimental taken from IR. We compare also our IR results concerning hydroxyl groups with 29 SI magic angle spinning NMR results of silicon atoms in the zeolite frameworks. I shall present an example of such comparison. The acid strength of bridging hydroxyls in zeolites depends mostly on two factors, on geometrical factor and chemical factor. Geometrical factor is the geometry of the bridge, the bond distances, bridge angle value. The chemical factor is a number of aluminum atoms in the close vicinity of hydroxyl groups. According to Löwenstein rule, aluminum atoms can be connected through oxygens only to Si atoms. But Si atoms may be connected either to another Si or to Al. So the number of Al atoms connected to this bridging Si, the N number in this formula, determines the acid strength of bridging hydroxyls. Based on those considerations, we may say that homogeneous hydroxyl group, it means all of the same acid strength, would appear in zeolites in which all the hydroxyls have the same geometry, and also all the hydroxyls have the same number of Al atoms in the closest vicinity. In other words, N number is the same for all the hydroxyls. Both conditions must be true. On the other hand, heterogeneous hydroxyls are expected in zeolites in which we have hydroxyls of various bridge geometry, or there are hydroxyls of various number of Al atoms in the close vicinity of the hydroxyl. It means there are hydroxyls of various N numbers. we studied both zeolites in which bridging hydroxyls were expected to be homogeneous, like NaHA, NaHX, and zeolites in which hydroxyl groups were expected to be heterogeneous, NaHZSL5, NaHY. Now we are studying NaH monotherites. We studied heterogeneity of hydroxyl groups by IR spectroscopy, by the analysis of free hydroxyl band, and by the analysis of OH band, of the band of OH groups engaged in hydrogen bonding with aromatic hydrocarbons or olefins, or interacting with paraffins by permanent dipole-induced dipole interaction. If we have homogeneous hydroxyls, the IR band is narrow and not split. In the case of heterogeneous hydroxyl groups, the IR band is broader, asymmetric, and split. In most cases, this splitting can be seen only after the calculation of the second derivative of the spectrum. The values of frequency shifts were used to calculate the values of proton affinity of OH groups by using Bellamy, Hallam, and Williams relation. This is a linear relation relating the frequency shift of two acids. One of them can be considered as a standard. And if we know the proton affinity of the standard acid, we can calculate the proton affinity of the acid which is under the investigation. In our case, this acid under the investigation was the hydroxyl group in zeolites. Now, I will present very briefly the results concerning a zeolite. A zeolite has absolutely no importance for catalysis, but it's interesting for the studies of heterogeneity of hydroxyl groups because it's one of very few zeolites in which hydroxyl groups are expected to be homogeneous. Why? Because Si to Al ratio is 1. So we have the same number of Si atoms and Al atoms. So all the hydroxyls may be represented by this formula. The N number is 3. T atoms are crystallographically equivalent. All bridging hydroxyls have the same geometry. So bridging hydroxyls are expected to be homogeneous. This is what we expect. But those are the experimental results. This is a spectrum of hydroxyl groups in a zeolite forming hydrogen bonding with ethylene. The shifted band is relatively narrow and not split, thus indicating that bridging hydroxyls are really homogeneous. And now, the results concerning ZSM5 zeolite. In this zeolite, Si to Al is about 50. Aluminium atoms are strongly diluted by Si. So all the hydroxyls have this, may be described by this formula. Have only one Al atom in this. The N number is 0. But T atoms are crystallographically non-equivalent. There is 12 T atom positions. TOT bond angle may vary from 140 to 177 degrees. So bridging hydroxyls are expected to be heterogeneous in ZSL5. Those are the results. This is a spectrum of our hydroxyl NaHZSL5 perturbed by hydrogen bonding with the same ethylene. The shifted band is broader and asymmetric. We studied the heterogeneity of hydroxyl groups in ZSL5 zeolites, not only by the sorption of ethylene, but also by the sorption of other hydrocarbons. We used benzene, toluene, paraxylene, we used hexane and hexane, which interacts with hydroxyl groups by permanent dipole-induced dipole interaction. We use also chlorobenzene and fluorobenzene. In this picture, we have the results obtained with chlorobenzene solution. We have 4 spectra of hydroxyl groups engaging hydrogen bonding with chlorobenzene. Those 4 spectra correspond to various amounts of chlorobenzene salt, to various percent of hydroxyl groups engaging hydrogen bonding. So we see that the band is asymmetric and composed of few submaxima. This is the result. This is the second derivative diagram. We see 1, 2, 3, 4, and 5 minima in the second derivative diagram, suggesting that you have 5 submaxima. This is the result of band. Those results were obtained with chlorobenzene. We obtained very similar results with other hydrocarbons, other molecules. In all the cases, the shifted band was split into few subgroups. So we can say that the 5 kinds of bridging hydroxyls of various acid strengths, the proton affinity values were calculated from Bellamy-Hallam and Williams relation, and you obtained for the less acidic hydroxyls, denoted as OH1, 1316 kilojoules per mole, for the most acidic, 1197 kilojoules per mole. Now, I will present you the data concerning 4 results. In 4 results, T atoms are crystallographically equivalent. All hydroxyls have the same geometry, but there may be hydroxyls of various amount of Al atoms close to the edge. The situation is different in X zeolite and in Y zeolites. In X zeolites, of Si2Al close to 1, the situation is similar as in A zeolite. You have the same number of Si atom and Al atom. All Si atoms are surrounded by 4 aluminums. In NMR spectrum, magic and spinning NMR, we have 1 signal of Si having 4 aluminum layers. All the hydroxyls may be represented by this formula. So in X zeolite, hydroxyl groups are expected to be homogeneous. In Y zeolite, in which Si2Al is close to 2 and 5, we have 4 NMR signals. Of Si having 3 Al neighbors, 2 Al neighbors, 1 and 0 Al neighbors. Si having 0 Al cannot create bridging hydroxyl. There must be a pair of Si and Al. We expect 3 kinds of bridging hydroxyls that are represented by such 3 formula. This one corresponds to this Si species. We get 3 Al now, neighbor 1 and 2 together 3. This formula corresponds to this Si species, and this formula to this Si species. So in the case of Y zeolite, we expect 3 kinds of bridging hydroxyls of various acid strengths. And now the IR data. Those are the spectra of hydroxyl groups engaged in hydrogen bonding with chlorobenzene. In the case of X zeolite and in the case of Y zeolite. In X zeolite, and those are second derivative diagrams. In the case of X zeolite, in the second derivative diagram, we see 1 distinct minimum, thus suggesting that you have 1 kind of bridging hydroxyls. In Y zeolite, in the second derivative, we see 3 minima, suggesting that you have 3 submaxima in this spectrum. This is the result of it. So the results obtained with chlorobenzene sorption and also with the sorption of other hydrocarbons, other molecules like benzene, toluene, xylene, fluorobenzene, bring to conclusion that in X zeolite we have homogeneous hydroxyls like expected, and in Y zeolite then we have three kinds of bridging hydroxyls. The results I just presented indicate that the results of NMR may be concerning skeleton Si atom may be well compared with the results of IR concerning bridging hydroxyls. According to NMR, we may have 5 kinds of Si species in zeolite, having 4Al, 3Al, 2, 1, and 0Al. And as only 4 of them can create bridging hydroxyls, we may have 4 kinds of bridging hydroxyls. And according to IR, such 4 kinds of bridging hydroxyls of various acid strengths have been found. At that moment, we decided to look for a quantitative correlation of NMR and IR data. NMR concerning skeleton Si and IR data concerning hydroxyl groups. We studied a series of 15 Foresites of Si to Al from 106 to 702. It means Foresites of various Al contents. And we know from NMR data that the proportion between the various Si species having various number of Al numbers depends strongly on Al content. So we expected that the proportions between corresponding them OH groups would change, would depend on the composition of zeolite in the same way. We made a parallel NMR study and IR study. NMR spectral were taken in Cambridge University, the IR were taken in our laboratory. Those are 6 of our 15 NMR spectra. We see 5 NMR signals. The signal of Si having 0 Al, this one which cannot create bridging hydroxyl is marked in black. We see that the proportion between those signals depends strongly on Si to Al ratio. This picture, this diagram, represents the percentage contribution of each of those these 4 kinds of Si species taken from NMR. This. And the lower diagram represents the proportion from between the percentage contribution of 4 kinds of bridging hydroxyls corresponding to those 4 kinds of Si species. Those data were taken from NMR. So in the case of X zeolite, this one, in which Si to Al is 1, we have only 1 NMR signal, we have only 1 Si species, the percentage contribution is 100%. We have only 1 kind of bridging hydroxyls, the less acidic, denoted as O1. The amount of this Si species, the percentage contribution of it, diminishes monotonously with Si to Al. The same concerns the percentage contribution of bridging hydroxyls, the less acidic, corresponding to those species. On the other hand, the percentage contribution of this species, of Si having 1 Al, increases monotonicity with Si to Al. The same concerns the percentage contribution of the most acidic hydroxyls denoted as SOH4. This is the blue line is a percentage contribution of Si having 3Al as neighbors to this signal. And the blue line in the lower diagram is a percentage contribution of corresponding then hydroxyl groups taken from IR spectrum. The green line is a percentage contribution of this signal of Si having 2Al, and this is the green line in the lower diagram, is a percentage contribution of corresponding then bridging hydroxyl taken from IR spectrum. We can see how good is the correlation between NMR data concerning skeleton silicon and IR data concerning bridging hydroxyls. Not only the shape of the line is the same, but also the absolute values are very close. For example, 60% maximal concentration of this Si species and 60% the maximal concentration of corresponding bridging hydroxyl. Such good agreement between NMR data concerning Si and IR data concerning hydroxyl groups indicates that at first our assignment of 4 kinds of bridging hydroxyls to 4 kinds of Si species was correct. But this agreement means also something else. Hydroxyl groups are active sites in many important for the catalysis reaction. And the information on the acid, on the hydroxyl groups of zeolites, on the acid sites on zeolites, may be obtained not only by direct studies of OH groups, for example by IR spectroscopy, but also by indirect studies of the properties of silicon atoms by NMR. Now, I shall present the last transparency concerning the deprotonization energies. This is a comparison between our IR data and the results of quantum chemical calculations. We know that you have 4 kinds of bridging hydroxyls of various amounts of Al close to the bridge. We can calculate the deprotonization energies by 2 ways. From IR spectra, by using Bellamy-Callard and Williams relation, those are the values. But we may calculate also the deprotonization energies by quantum chemistry. We made such a study. We use clusters of such formula. The cluster geometry was optimized with only one parameter constant, the bridge angle, 136.8. This value was taken from the paper of Olson and Dempsey. This is experimental value for bridging hydroxyls in photoscience. And the last diagram shows the comparison between the experimental data of proton affinity for 4 kinds of our bridging hydroxyls and the theoretical data, the lower line, obtained by quantum chemistry. The agreement is also very good. The values vary from 30 to maybe 80 kilojoules per mole. So, in conclusion, we may say the results concerning hydroxyl groups in zeolites may be well compared with NMR data concerning not only hydroxyl, but concerning skeleton silicon atoms, and also compared with the quantum chemical calculations. It was a short review of our results. The full complete of data is presented in a series of 10 papers. We have the publications concerning the heterogeneity of hydroxyl group in A zeolite, ZSM5 zeolite, and in photoscience. Thank you for your attention.
Are there questions? Yeah, Keith. In your comparison between the NMR results and the IR results, you found 4 different kinds of hydroxyl groups, but you didn't say how you distinguish those. Are those different IR frequencies?
Yes.
And how do you decide? Have you got an example or something?
Yes, I did not tell too much the details because of shortage of the time. I distinguished them by the frequency shift. By the frequency shift, when forming the hydrogen bonding with for example, aromatic hydrocarbons. For example, in this case, in X zeolite, the frequency shift is 100, and for benzene, it's 180. For those 3 kinds of hydroxyls in Y, we have from maybe 250 until 350 centimeters to -1. We distinguish them by the value of frequency shifts. This is the right answer. When forming the hydrogen bonding with certain molecules.
Yeah, as deduced by the second derivative of those curves, which are rather broad. The thing is, in a phlogisite, you got 4 different kinds of oxygens.
Yes. This is what I want.
And the OH frequencies, there are 2, those vibrating inside the cubocahedron and those vibrating in the big cavity.
Yes.
It's not clear to me how you can separate those.
Yes, I did not tell about it because of the shortage of the time, not to tell too much detail.
I should have given you some of my time.
Yes, okay. I shall tell about it now. We have 2 distinct infrared peaks like you presented in your transparencies in Forges. One corresponds to O1H, and the second one to O3H. We know that we have 4 kinds of oxygens. And all the results I presented in my talk today concerns only OH, O1H.
O1H.
Those ones which are accessible to all the molecules. I did not tell about it to make my talk shorter and not so, let's say, complicated. Not to give too much detail, but perhaps just this information should be presented.
I think at this point we're going to have to cut off the discussion. It can be certainly carried on in the hallways. Our next speaker is Professor Robert Greenler from the University of Wisconsin-Milwaukee, and his topic is the origins of multiple bands in the infrared spectra of CO adsorbed on metal surfaces. Bob.
On the sodium positioning of H groups, and I try to relate those results with the problem. I don't say.
This does stir up some memories coming back, and hearing Keith's comments makes me remember that Gordon conference, which you say was 64, in which Keith essentially invited everyone in the world who had published a paper on the infrared's investigation of adsorb molecules, and most of them came. I'm just curious, how many of you here were at that Gordon conference in 64? 1, 2, 3, 4, 5, 6, yeah, I see. Not quite as impressive a turnout as Woodstock, perhaps. But quite interesting. I had I come from a physics background. I had done my graduate research on something entirely different, and afterwards decided that there was a fruitful area here to which to apply infrared spectroscopy, which I knew a little bit about. I developed this essentially by myself, tried to teach myself something about this, and when I got to this Gordon conference, I talked a little bit about the alcohol work that Keith mentioned, the alcohols on alumina. And I remember the question, which may have been Keith's, I don't know who answered it, saying everyone knows that alumina dehydrates alcohols, and according to your work, it looks like it should dehydrogenate it. Why is that? And I remember shrugging my shoulders and saying, well, that's the way the spectra, I interpret the spectra, and I felt like I was a stupid physicist standing naked in front of this group of chemists. Now, I've never quite gotten over that feeling. But as you see, I continue to do it and to risk and do the best I can in talking to chemists. Let me introduce my co-author, Kurt Brandt, who is the source of a number of the insights that I'm going to talk about today. And what I'm going to do is discuss a situation where we adsorb one kind of simple molecule on a metal surface, CO, and look at a multiplicity of bands which come all from the CO stretching vibration. And what I'm going to do is to try to give you some physical insight into the source of those bands. That is, I'm going to try to give you our physical interpretation rather than the evidence for it. First, the big picture. You put a CO molecule onto a metal surface, and in a sense now you have an entity, a molecule which includes the surface. And what we tend to call the CO stretching vibration really is a normal mode of this surface, a normal mode of vibration of this surface. And the frequency of that normal mode, which for convenience we call CO stretching, really involves the whole entity. And so if you change another part of the entity, you change the CO stretching vibration. And so the first picture is one which appropriately dates to the paper which started all of this. And you see some bands which come from putting a CO molecule linearly bonded to a surface atom. We see some other entities or other bands that come from CO molecules bridge bonded to 2, and some others that result from bonding to 3 or more. Now, something that I'm going to emphasize as I discuss several of these effects is the magnitudes of the differences. These 3 kinds of bonding situations give bands in positions that differ by about 100 wave numbers, 100 reciprocal centimeters. And that's going to be significant in some of the other things that I'm going to discuss. From now on, I'm going to talk about the situation where you get several or a few infrared bands, all of which come from what we'll call the CO stretching vibration, linearly bonded to a surface metal atom. Now, most of us who have been in this business a while have succumbed to the temptation to say, you see 3 bands and there are 3 different crystal sites, this face, that face, an edge, or whatever. And most of us have succumbed to that and gotten it wrong. So one of the objects of my talk today is to try to convince you that in general that's not a viable interpretation, and you have to look elsewhere to explain these multiple bands. Let me consider the crystal site effect first. I'm going to treat a few different effects. For platinum, and presumably for other metals, we find that the significant feature, the band position, when you adsorb linearly to a metal atom, is the coordination number of that metal atom in the surface. For instance, if you look at one of these atoms on the step edge, you see that it's surrounded in that layer by 4 atoms, and sits on 3 below, so it has a coordination number of 7. And essentially, the vibration frequency of the adsorbed molecule in that atom is determined by that coordination number of 7. And in fact, if you compare that then with the atom in an edge of a small particle, which also has a coordination number of 7, they both have essentially the same frequency, determined by that coordination number. Another similar example, if you have a kinked step surface where you have a coordination number of 6, you can have a similar site for adsorption and a similar CO vibration frequency as if you're in the corner of a particle, as I showed there. Next, let me consider the coupling between 2 atoms adsorbed nearby, or 2 molecules adsorbed nearby. If you have 2 oscillators which couple with each other, this is generally true in any coupled system of oscillators, you have a system now, and an appropriate way to look at that system is to consider its normal modes. You have one normal mode where these 2 oscillators are oscillating in phase, and another one where they're oscillating out of phase. In the molecular case, this in-phase system has a higher frequency than the out-of-phase. If you have n oscillators, you get n normal modes. So let me show you some simple models. Here n is equal to 5, and I show you 5 oscillators, and the numbers are picked to represent CO atoms on a platinum surface. And you see there are 5 normal vibrations, 5 normal modes, and we've plotted them out here, and the length of the arrow represents the magnitude of the motion of that oscillator. So there's a couple things to see here. This highest frequency mode has everything oscillating in phase. To see the strength of the infrared band produced by this mode, you want to look at the magnitude of the dipole that's oscillating with this mode. And you see everything oscillating in phase here gives a big dipole oscillation, and hence a big infrared intensity. The second mode has some of the CO molecules stretching and others contracting. The net dipole change accompanying that mode of oscillation is 0, and the infrared intensity is 0. That is, you can't excite a vibration with an electric field where there's no change in the oscillating, in the dipole moment that goes along with that vibration. So in fact, you see that where this has an intensity of 1, the maximum intensity of the others is 5% of that. So essentially, you might say, with this, all you would see is one band, and it would be shifted up about 10 reciprocal centimeters from the isolated molecule. And in fact, here we see how it shifts as you increase the length of the chain, and the shift is the order of 10 reciprocal centimeters when you have a few atoms together. Now we can do the same thing with a two-dimensional array, which I show here. And again, you see the highest frequency mode is the one where everything is vibrating in phase, and the different modes vary by about 10 reciprocal centimeters. But this is the only one that has any appreciable intensity. The highest, the next one that's highest has 4% of that. And you see that when you talk about the number of atoms here, that the shift from coupling is greater because a particular molecule has more nearest neighbors when you're packed in a two-dimensional array than when you're spread in a one-dimensional array. Again, I want to emphasize the shift, the magnitudes of the shifts. As we go from one mode to the other, the shifts vary, the frequencies, wave numbers vary by 5 or 10 wave numbers, and the kind of shifts that you get for a few molecules put together is the order of 10 or 20 wave numbers. I've shown you cases and said in each one of these cases I show, and I could show you many more where this is also true, that the only significant intensity infrared absorption is connected with the in-phase vibration. And so you might say, so why am I telling you all this stuff about the other vibrations which don't contribute anything to the infrared absorption? And the answer is, because sometimes they do. For instance, let me give you one example. Suppose you adsorb these molecules around a small particle. The highest frequency mode is the one where they're all oscillating in phase. That is to say, all the molecules are stretching at the same time. And you look at that, the net dipole change in this case, where you've wrapped the chain around a molecule, the net dipole change is 0. And so in that case, you won't see that mode. The second mode, about 10 wave numbers down, is this one where the ones on top are stretching, where the ones on the bottom are contracting, and it means they're all doing this together. And that's the mode where most of the intensity is. So there's a case where sometimes you may have one mode oscillating and sometimes another mode, and the difference is about 10 wave numbers. So I've given you 3 examples of the ways in which a number of identical molecules adsorb so they can interact with each other, form a coupled system. Now, what I have said, and I want to emphasize again, I think a significant and a fundamental way to look at this system is to look at it as a system which has a number of normal modes. And each of the absorption bands, the infrared that you get from that system, is one of the normal modes of that coupled system. All right, you know, to get strong coupling, you need to have the frequencies of oscillators fairly close together. For instance, if you park a linearly bonded CO next to a bridge bonded CO so that their wave numbers differ by 100 reciprocal centimeters, let's say, there's a system and it has 2 normal modes where they vibrate in phase and out of phase. But you'll find that in this case, in one of those modes, the frequency is almost the same as one of the molecules, and the other one is not participating much in that mode. And in the other mode, the frequency is essentially the mode of the independent other molecule, and this one is not participating much in that mode. So if their frequencies are far apart, they don't interact very much. Now, here's an important point of what I'm trying to develop today, is that a number of these effects that I've showed you all produce shifts of the order of 10 wave numbers. And so you can get groups of one kind of molecule coupling up and shifting their frequency until they can couple with a different kind of vibration. Now, rather than try to make that clearer in words, let me Let me give you an example of what I'm trying to say. This is a hypothetical example. Don't take it too seriously, though I will relate it to something I'll show you later. Suppose this is a terrace in a stepped surface, in a 100 surface, and here's the edge of the terrace. If we adsorb a CO molecule on the terrace, or some that are widely separated, it'll have a frequency of about 2077, an isolated terrace, molecule in the isolated terrace. If I adsorb a molecule on the step, which has a different coordination number, the isolated frequency is about 2067. If I populate that whole step edge with a linear array, the linear array the interaction will raise that in-phase mode, which I showed you, up to about 2077. So now with that coupling, this system has the same frequency as these isolated terrace atoms, and so they will strongly couple together. And there'll be a strong interaction. Now, let me put that in normal mode language. I would say that there should be a strong normal mode which consists of all of these molecules vibrating in phase together, producing a strong infrared band. So I'm going to show you two examples of systems where I think we can get some intuitive understanding by this kind of shifting and coupling. We've looked at CO on platinum particles, two different samples which have different mean particle sizes. There's a distribution, but the mean of one of these is 11 and the other is 39 angstroms. And when you adsorb CO on those two different samples, you get very different spectra. These are experimental spectra. First, let me try to see if we can make some sense out of the spectrum for the smaller particle. Now here, I have a table up here in which I show the wave number of an isolated adsorbed molecule. And now this, I want to emphasize this. This all comes from analysis of extended single crystal data with the reflection absorption technique, not our work, but work from the literature. And you see, depending on the coordination number, you get different wave number, and varying linearly with coordination number with steps of 10 reciprocal centimeters. So we're going to apply this to the small particle, and our model particle is 112 angstroms in diameter, which has a very nice shape. In fact, most of the atoms in that molecule are corner atoms. If I cover that molecule with, or that little crystal with CO molecules spaced square root of 3 times a platinum diameter apart, you can get 12 molecules on it, all of which are on the corners. So this is what I understand down here, or I should say we understand down here. This is our calculated spectra, and we only understand things up here insofar as we can predict them from what we calculate. So what we've done is calculate normal modes for different arrangements. When we get a normal mode, with a certain intensity. We represent it by a Lorentzian band with a bandwidth of, I believe, 14 reciprocal centimeters, which to match our spectra, I think there's some evidence that we have something like a 12 reciprocal centimeter bandwidth plus another 2 instrumental contribution. When we put 6 CO atoms on here, on the corners, we're starting off with something 2057. And we get that from the extended surface data. Coupling takes that up about 10 reciprocal centimeters. And so we have something, say, which extends over, some of each of 2 centimeters. And the second mode, we're not looking at the all-in phase mode. The second mode down drops that back another 10 reciprocal centimeters. And so we end up with a mode here at about 2060, which is that band right there. Now, if you have the same bunch of molecules spread over let's think of it spread over 2 hemispheres, there is another mode. It's going to be weaker. I think I said that wrong. The higher mode is the in-phase mode. The strong mode here is the one where those in the upper hemisphere are going up and those in the lower hemisphere are also going up. That is, some of them are out of phase with the others. That's the strongest mode, and that's the one at 2060. So let me say that again. We've started off with something at about 2057. By coupling, we've shifted it up about 10 reciprocal centimeters. Since we've not used the high mode, but the second one, we've dropped it back down 10 reciprocal centimeters, and we end up at about the same position we started with, actually about 2060. The in-phase mode, when you don't have a complete layer, is there, weaker. It's been shifted up by the coupling, but not down because we're still in that highest mode. And so that gives a band here. And of course, the interest in that is because it looks like the spectrum here for particular coverage, the experimental spectrum. If we put 12 molecules on there, saturate the surface, this second mode shifts up a few reciprocal centimeters, and the first mode now disappears. That is, where everything is in phase, stretching, no dipole moment. And the experimental spectra hasn't quite disappeared. And that's not surprising, because if instead of 12 you put 11 or 13, you still get it. If your particles are a little bit asymmetric, you'll still get a trace of what, in the perfect case, would be a symmetric vibration with no dipole change. So I think we understand something about where those bands come from. If we look at the bigger particle, and again, we're starting off with data which comes not from the small particles that we're trying to interpret, but it comes from the extended single crystal data. If we look at the case where we have 13 atoms, 13 molecules placed on here, and what we did was start putting them around a corner and expanded them out into the faces. And 13 molecules here is our placement, you see, which is represented down here. This is going to be the model spectrum, the spectrum that we're going to deduce from this. For those 13 molecules, if we look at the normal modes of them, there are 3 normal modes that dominate everything. The ones I've shown you here, they have 85% of all the intensity, the rest divided up between a lot of minor modes. The one that's the lowest frequency is nothing much is participating except these 3 isolated molecules, which you see are molecules adsorbed on edge sites, whose frequency on the extended single crystals are 2067. They're far enough away in this normal mode that they don't couple, and the frequency of that normal mode is 2067. The next mode here is one where these three molecules, which are also on edges, but they're in a little cluster, coupled tightly, which will raise their frequency from 2067 about 10 reciprocal centimeters, let's say to 2077, which then puts it the same as the frequency of an atom in a 1-1-1 phase, namely that one. Now this is similar to the example I showed you. So that these all couple together, and with the addition to the party of this 100 molecule pushes the frequency to about 2080. The highest mode is one where you have strings of atoms or molecules here, which you see are on 1-1-1 sites. We start at 2087. It gets shifted up by somewhat by their coupling, but you also have some contribution from these edge molecules on edge sites tightly coupled, which has shifted them up, as we've seen, to about 2077. So all of these couple together and give a frequency at about 2090. Now, I mean, we've continued to expand, and you see we get these model spectra, which look almost embarrassingly similar to the experimental spectra. And the point that I make here is there are three bands and three main sites, and you get it wrong if you say one band for each site. This band comes from isolated molecules on isolated edge atoms. This one comes from molecules closely coupled edge atoms plus one in a 100 position that are oscillating together. And this one is a combination of molecules on 1-1-1 sites plus tightly coupled edge sites. The normal mode description tells us this. And insofar as we can reproduce these, we know what these bands come from. So, where do we go with this? I think probably it was about 25 years ago when Keith Hall started to complain that you physicists are still working with CO. When is it that you're going to start working on some interesting molecule? Well, Keith, the emphasis here is not on the CO, but the emphasis here is on the surface. If we can interpret absorption on these small, the infrared spectra on these small particles by saying, by interpreting these bands in the way I've talked about it, it would seem that we're well on our way to being able to take the spectra from a dispersed CO adsorbed on a dispersed metal and tell you something about the number and kinds of sites on the metal and the size of single crystal facets. And the casual observer who comes from a background not of chemistry might think that kind of a description of what the surface consists of, sites, patches, correlated with the results of different catalyst preparations and the corresponding different catalyst actions, casual observer might think that could be useful information.
I think we take time out. One quick question, and that's it.
The particular array of CO that you used is this very interesting triangular array. I think it was centered on an apex of the platinum crystal.
Yes.
And of course, the calculated spectra and the theoretical spectra, or the experimental spectra, agree. Do you believe then that that type of absorption, avoiding the faces of that crystal, is likely to be the real way that the CO fills the site?
Sure, yes.
That's what
And,
you have to conclude.
yeah, and
Why would that be?
well, I mean, we're led to that from the work on the stepped crystals, where first you adsorb along the edges rather than on the faces, and after you essentially saturate the edges, then you start adsorbing on the terraces. Similar behavior.
Yeah, this is an extremely interesting